Welcome to ScaleUp University. Welcome to the course on designing data intensive applications. So this is the lecture number 10 of module 1, and in this lecture we will be discussing what does scalability really mean. So what exactly is the meaning of scalability? That is what we will look in this lecture. So if we look at the lecture overview, like what exactly we will be covering in this lecture. So if we consider a statement like our system can handle millions of users. Now this statement, it looks very impressive because it gives us an idea that, okay, we are talking about a computing system which can handle millions of users. But this statement is meaningless without context. Like this statement is ambiguous. And why is it so? Because now if we say millions of users, so millions of users doing what? Like in this statement, the load is not clear. The load is not properly defined. Like millions of users, what they are doing, they are streaming something, or they are just sending the request and getting a response. At what time? Like millions of users, are they accessing the system concurrently or sequentially? So that information is missing in this statement. With what latency? Because this statement is telling that our system can handle millions of users, but still the latency is not clear, and with what consistency guarantees. So a statement like this, our system can handle millions of users, it sounds impressive, but it is incomplete, it is ambiguous, because it does not contain some very critical information. And this statement, like using this statement, we cannot comment on the scalability of the system. So scalability is not a label. Scalability is not a label. Rather, scalability is a behavior under increasing load. Scalability is a behavior under increasing load. Like when the load increases, how the behavior of the system changes. So scalability is the behavior of the system under increasing load. If the system can handle the increasing load efficiently, we call the system to be scalable. So that is what this lecture is about. So this lecture is a transition from reliability to scalability. And this lecture fixes one of the biggest misconceptions in system design. And that is, scalability is not about how fast your system is today. So scalability is not about the speed, the performance of the system. Scalability is not at all about how fast the system is today, but it is about how your system behaves as the load increases, as the demand grows. So now it's very clear to us that, okay, if I talk about scalability, the meaning of scalability is that the behavior of the system under increasing load, how the system behaves as the demand grows. If the system continues performing efficiently as the demand grows, we call the system to be scalable. Otherwise, the system is not scalable. So that is the true meaning of scalability, and that is what we will discuss in some good detail in this lecture. So if we look at the topics that we will cover in this lecture, so we'll discuss what is scalability, scalability versus performance, the difference between the scalability of the system and the performance of the system, scalability versus the efficiency, the difference between the scalability of the system and efficiency of the system, why handles millions of users is meaningless, why statements like the system can handle millions of users, these statements are meaningless. So we will understand the reason for that. Then we will discuss scalability as a growth story. Bottlenecks define scalability. And finally, we will conclude this lecture by discussing horizontal scaling versus vertical scaling. So all these topics we will cover in this lecture itself one by one. So first we will look at what is scalability. So if we talk about what exactly is scalability, so a system is said to be scalable if it can handle increase the load by adding resources without unacceptable degradation in performance or correctness. So scalability of the system means if the system can handle increase the load by adding resources without unacceptable degradation in performance or correctness. So the system is scalable if it can handle the increasing load. So that is the meaning of scalability. So let us suppose in a system, if the load is increasing, and when I talk about load, increasing load, the meaning of increasing load is increasing the number of users, increasing the data, and increase in the request. So when I talk about scalability, three important components are there in this definition. The first component is the increasing load. So when the load on the system is increasing, and when I talk about increasing load, I am talking about increasing number of users, increasing data, and increasing number of requests. So that's the increasing load. So when the load increases by adding resources. Now adding resources is the second very important component in this definition of scalability. And when I talk about adding resources, I'm talking about adding more compute, adding more memory, and adding more network bandwidth. So increasing load, adding more resources, if the system maintains acceptable performance. So this is the third component in the definition, that is maintaining the acceptable performance. And maintaining the acceptable performance means maintaining the speed, maintaining the reliability, and maintaining the correctness. So a system is said to be scalable if it can handle increase the load, that is the increase the users, increase the data, increase the user request by adding resources, by adding more compute power, more memory, more network bandwidth, and without unacceptable degradation in performance or correctness, or maintaining acceptable performance. So system can handle the increased load, maintaining the acceptable performance, like maintaining the speed, reliability, and correctness. So this is the scalability. Scalability versus performance. If we look into the difference between the scalability versus the performance, so if we look at performance of a system, so performance of a system is how fast the system is right now. Performance of the system is the how fast the system is right now. So performance, it is measured in latency, response time, and throughput, that is jobs per second. So performance is how fast the system is right now, and performance is measured by the latency, the response time, and also the throughput, that is the jobs executed per second. If we look at the example of performance of the system, so we have a system A that handles 1000 like 1000 users at 10 millisecond latency, and it breaks at 5000 users. So we will get back to the example after discussing the scalability first. Now we will discuss the scalability. What is the scalability of the system? So scalability means how performance changes or how the system behaves as load increases and resources increases. So how performance changes as the load increases and resources increases. So a very important key insight, see, a system can be fast but not scalable. A system can be fast but not scalable. Meaning to say that a system can be fast right now, but it cannot handle the increased load. So that is what a system can be fast but not scalable. And on the other hand, we can have a system that can be slow but scalable. A system can be slow but scalable. So that is what the key insight is. Now let us look at an example to understand the difference between scalability and performance. So we are discussing an example which will demonstrate the difference between scalability versus performance. Like we already saw that we can have a system that can be fast but not scalable. We can have a system that can be slow but scalable. So for example, I have a system A. Now this system A, it can handle 1000 users at 10 millisecond latency. But if we increase the user, if we make the increase user as 5000, if 5000 users try to access that system, it breaks. So this is an example of a system which is fast but not scalable. On the other hand, we can have a system B which handles 1000 users at 50 millisecond latency. 1000 users at 50 millisecond latency, and it can scale to 1 million users smoothly. So here the latency is more. So system B is an example of a system which is slow as compared to system A, but it is scalable because it can handle 1 million users. But system A is fast, but it is not scalable. Like once the system got 5000 users, it start breaking down. So scalable systems are better in the long run. So system B is scalable and it is better for the long run. So the important takeaway is performance is a snapshot. Performance is a snapshot. Scalability is a trajectory. Performance is a snapshot. Scalability is a trajectory. So performance is something which is the current state of the system. Like in the current state, like right now, how fast the system is. So that's the performance. And scalability is something which has to do like the long term. It's like a trajectory, like as the load is getting increased, how the system is behaving. So that's the scalability. So performance is a snapshot, scalability is a trajectory. Now we'll discuss scalability versus efficiency. So now let us look at the difference between the scalability and efficiency. So if we talk about efficiency, if we talk about efficiency of the system, so what is the meaning of efficiency of the system? Let us understand. So efficiency of the system means resource usage per unit work. So if the resource usage per unit work is less, the system is said to be efficient. And when I talk about resource usage per unit work, I am talking about CPU usage per request. I am talking about memory usage per request. I am talking about cost per request. So in order to make the system more efficient, the goal is to minimize the resource usage. So an efficient system is the one which will be using minimal resources per unit work. So that is the meaning of efficiency of the system. So efficiency of the system is resource usage per unit work. So that resource usage is can be CPU usage per request, memory usage per request, cost per request. If we talk about the scalability of the system, so scalability of the system is the ability of the system to handle growth by adding more and more resources. Scalability of the system is the ability of the system to handle growth by adding more and more resources. So the goal of scalability is to handle growth. Handle growth means to handle increasing load. So as the load increases, by adding more resources, we should be able to maintain the performance of the system, and that is the core essence of scalability of the system. A scalable system is the one which can handle the increasing load by adding more and more resources. Now we will look at a very important trade-off. So there is a trade-off between the efficiency and the scalability. So see, efficiency, it focuses on minimizing the resource usage or minimizing the waste, minimizing the resource usage. But scalability is something which focuses on the growth. So scalability is all about growth and efficiency is all about minimizing the resource usage. So see, what happens is that when we try to make system scalable, we are making the system less efficient. Why? Because to make system scalable, we are adding more and more resources, and ultimately resource usage per unit work will increase because the load is increasing. I am adding more and more resources, so resource usage per unit work is increasing. The system is becoming less efficient. So if we try to make the system scalable, we are reducing the efficiency, and if we are trying to make the system efficient, minimizing the resource usage, we are making the system less scalable, because for efficiency we have to use less resources. Like the core essence of efficiency is to get the work done by using the minimal resources. So here one representation is there, like I'm just using two CPUs to get the work done. So it can handle limited load. But scalability means I will keep on increasing the resources so that I can handle more and more load. But here I am increasing the resources. So resource usage is increasing. So efficiency is decreasing. So trade-off is now very clear that efficiency and scalability, they are like trade-offs. If I try to increase the scalability of the system, efficiency of the system will go down. And if I try to increase the efficiency of the system, then scalability of the system will go down. So this is a very important trade-off. So from this trade-off, we can consider one very important insight. A system can be scalable, but inefficient. So now it's very clear that we can have a system that is scalable, like it is having lots and lots of resources, but since it's having lots and lots of resources, it is inefficient. So a system can be scalable, but inefficient. So if we look at an example, so we can scale by adding 100 more servers. Like in a system, we can add 100 more servers, but if each request wastes CPU, cost explodes. Because to make the system scalable, we have to add more resources, and because of which resource usage is increasing and the system is becoming less efficient. So now we will look at a real world reality. So see, the idea is that like when you will be designing a system, what should you prefer? Should you prefer scalability or efficiency? Because scalability means handle the growth, handle the increase the load, and efficiency means minimizing the resource usage. So it's a very important question in front of you, because we already saw there is a trade-off. Both cannot coexist. You cannot have a scalable system which is very efficient. So there is a trade-off exists between the scalability and efficiency. So what we should choose? So in real world, like when you will be doing the system design for early stage systems, you should prioritize scalability. So a very important learning: for early stage systems, prioritize the scalability, and for mature systems, optimize for efficiency. So the idea is that when you're just starting, so for early stage systems, just prioritize the scalability, just make the system working so that it can handle lots and lots of growth. And once the system scales, you can focus on optimizing the system, wherein you can eliminate the, or you can minimize the resource wastage, resource usage wastage. So that is the optimize for efficiency. So now it's very clear that as a system design engineer, Our goal is to first prioritize the scalability, make the system working, and then we can optimize for efficiency. Why handles millions of users is meaningless. So now we will look at like why statements like system can handle millions of users is meaningless. So why such statements are meaningless? Let us try to understand that. So what exactly is missing in that statement? So see, system can handle millions of users. It's like a vague statement. Many important crucial information is missing from that statement. Like that statement, it ignores the concurrency. That's this statement. It ignores the concurrency. Like are users active simultaneously? Are users active because handles millions of users? This statement is not telling anything about the concurrency, whether those millions of users, whether they are accessing the system simultaneously or sequentially. It might be thousands of users might be active simultaneously and not 1 million. So this crucial information is missing. The crucial information about the request patterns is missing from that statement. Like nothing is mentioned about the read versus write. Like system can handle millions of users. So whether we are talking about reads or writes, heavy or light operations, so all these crucial information, that is a request pattern, is missing. Like the system can handle complex queries or simple fetches. So system can handle millions of users. This statement, it is missing the concurrency aspect, the request patterns, and also the latency expectations. Latency expectations. Like that statement is telling nothing about the latency of the system, like whether the latency is 10 milliseconds or 2 seconds, whether the system is real time or batch processing. So latency expectation, it's a very crucial information that is missing in statement like system can handle millions of users. Even data size, information about the data size is missing. Like systems can, like the system can handle millions of users or system handles millions of users. This statement, it is telling nothing about the size of the data which the system can handle, like whether the system is dealing with kilobytes of data or the terabytes of data. So the storage information is completely missing from that statement, and the transfer impact is missing. And statement like system handles millions of users, it also lacks information about the geographic distribution. Geographic distribution. Whether the system is present in a single region or it is distributed globally. So crucial information about the network latency and compliance is also missing from that statement. So now it's very clear that statements like system handles millions of users, it looks very impressive, but it tells nothing like meaningful about the system, because such statement concurrency aspect is missing, request patterns is missing, latency expectation is missing, data size is missing, geographic distribution is missing. So this is a meaningless statement. So we should not get trapped with such statements. Rather, in order to convey the quality of the system, we should better ask questions. So in order to assess the quality of the system, we should ask questions like request per second, like how many requests per second the system can process, what is the peak load, what is the average load, what is the read write ratio, data growth rate, latency percentiles, whether it is 95 percentile, 99 percentile. So these are the right metrics. So in order to measure the system, we have to ask right questions, and these are the right questions, like request per second. So these are the right metrics. which we should consider: request per second, peak load versus average load, read write ratio, data growth rate, latency percentiles. If we look at an example, like we can come across statements like system can claim that it supports 1 million users, but in reality it is supporting only 1000 concurrent users. So here we can see the marketing versus engineering truth. Here we can see the marketing versus engineering truth. So the core insight which we should consider is scalability must be defined in terms of workload, not users. So now it's very clear that whenever we talk about the scalability of the system, we should ask the right question. We should focus on the metrics, and that those metrics are dependent on the workload and not the number of users. So whenever we are talking about scalability of the system, we should ask questions like how many requests per second the system can process, what is the peak load and the average load which the system is handling, what is the read write ratio, the data growth rate, latency percentiles, 95 percentile, 99 percentile. So these are the right questions which we should ask. Scalability as a growth story. So if we look at the scalability as a growth story, so scalability is about evolution over time. So scalability is all about handling the increasing workload. So scalability is about evolution over time. The system should have the capability of evolving over time. So a system by default, it is not scalable. So a system is not scalable by default. It becomes scalable through iterative design, iterative redesign. So see, the idea is that we always start with a small system and then we will keep on redesigning it. We will keep on adding more and more resources. So a system becomes scalable through iterative redesign, through architectural evolution. System becomes scalable through architectural evolution. System becomes scalable through learning from bottlenecks. Through learning from bottlenecks. So now it's very clear that a system by default it is not scalable. System becomes scalable through iterative redesign, architectural evolution, and learning from bottlenecks. And that is what scalability is about, evolution over time is. Now let us discuss the stages of growth in a scalable system. So if we talk about stages of growth, the first stage is the single node system. Now single node system, definitely it is very efficient, it is simple, it is fast, but it is limited scale. It cannot handle lots of workload, load it cannot handle. So it is simple, fast, efficient, but it's not scalable. Then what we do is the stage two is vertical scaling. So this single node system, we add more compute power, more memory to it. So that is the vertical scaling. So stage two is the vertical scaling, wherein the single node system, we make it more powerful by adding bigger machines, more CPU power, RAM power, and limited ceiling. And stage three is the horizontal scaling. So here what we do is in horizontal scaling, we will make use of multiple machines. Instead of using single machine, we will in horizontal scaling, we will add more and more nodes. So we will get distributed system and we will achieve load balancing. So the stage three is the horizontal scaling. Stage four is the distributed architecture. In the stage four, we will achieve distributed architecture wherein we partition the data across multiple nodes. We adopt the concept of replication and complex coordination. And stage five is the global scale. Stage five is the global scale. So here, multi-region deployment. So in global scale, what we will do is we distribute the Distributed architecture across the globe. So multi-region deployments we do. We will optimize for latency. So if somebody is accessing from North America, so they will be requesting the resources over there. So we will optimize the latency and consistency trade-offs. So this is the stages of growth. So we start with single node system in stage one to vertical scaling in stage two, wherein we add more compute power to the single node system. And in stage three, we consider horizontal scaling, wherein we replicate more powerful nodes. And stage four is distributed architecture, and stage five is the global scale. So these is the stages of growth for scalable systems. So in this way, scalability, it grows with time, it evolves over time. Now let us look at one very important insight. So from these stages of growth, one very important observation we can make is from day one, we don't design for 1 million users. So you don't design for 1 million users on day one. Rather, you design for growth path. And that we already saw the growth path, the stages of growth. So scalability is all about the ability to adapt. As the load increases, the system should able to adapt. So scalability is the ability to adapt. So a scalable system, it evolves architecture, it handles increasing complexity, and it adapts to changing workloads. It adapts to changing workloads. So that is what scalability is all about. So bottlenecks define scalability. Bottlenecks define scalability. So scalability, it is limited by, so if we talk about scalability, so bottlenecks define the scalability. So scalability is limited by CPU bottlenecks. Scalability is limited by the CPU bottlenecks. So compute intensity. So processor at 100% utilization. So compute intensity occurs when the processor reaches 100% utilization. When the processor is fully occupied, 100% utilized, then uh, what will happen is that we will reach the stage of compute intensity. For example, when we are performing intensive tasks like image processing, encryption, or complex algorithms, there this compute intensity plays a role. This compute intensity plays a role. Queuing. So when the CPU is maxed out, it cannot process incoming requests fast enough, forcing them into a queue and leading to increased latency and timeouts. So what is queuing? Queuing, see, the idea is that when the CPU is maxed out, like when 100% of the CPU is utilized, compute intensity we reach, it cannot process incoming requests, and we have to maintain a queue which will contain the incoming request. And it will lead to increased latency and timeouts. And here one very important law is there, Amdahl's law. This law, it states that in parallel processing, scalability is limited by the portion of the code that must run sequentially. Because if the code has to run sequentially, we cannot make use of it in parallel processing. So in parallel processing, scalability is limited by the portion of the code that must run sequentially. Even with more cores, the serial part of the task remains a fixed bottleneck. The serial part of the task, it remains a fixed bottleneck. So this is the CPU bottleneck. So now it's very clear that, see, the idea is to make the system scalable, but some limitations are there. And if we talk about the CPU limitations, thing is that when the load will increase, CPU will become compute intense. Like CPU will be fully utilized, and for more incoming load, we have to maintain a queue which will hold those requests, and hence it will increase the latency. So that is the CPU bottleneck. And also, if the process, it involves sequential code, then because of the Amdahl's law, we cannot achieve parallel processing. So the serial part of the task remains a fixed bottleneck. So these are the CPU bottlenecks which limits the scalability. So scalability, it is also limited by the memory. So if we talk about the memory limits of scalability, addressable capacity, addressable capacity. So the idea is that every system has a physical limit on RAM. RAM is limited. Once the RAM is fully occupied, the system cannot handle more concurrent user session or large data structures in memory. So that is the addressable capacity. So memory limit is a bottleneck because when we keep on increasing the load, after a point of time, the memory will get fully occupied and no more concurrent users or large in memory data will be supported. And then what we have to do, we have to do this disk swapping. In disk swapping, what we do is when the RAM is exhausted, RAM is fully occupied, the operating system uses swap or paging, wherein it moves the data to much slower disk. This drastically reduces performance and can lead to a thrashing state where the system spends more time moving data than processing it. And what will happen is when the load is continuously increasing because of the memory limits, uh, the RAM will be fully occupied and disk swapping will be done, wherein some chunk will be stored in the hard disk and from there it will be sent to the RAM when processing will be done. So disk swapping will be more as compared to processing. System spends more time in disk swapping rather than processing. So that will degrade the performance. And in languages like Java technology, we have garbage collection. So high memory pressure, it triggers more frequent and longer garbage collection pauses, which can halt application execution and kill scalability. So now it's very clear that scalability is limited by memory limits because memory is limited. So when we keep on increasing the load, after a point of time, RAM will get exhausted, because of which disk swapping will be involved, which will significantly degrade the performance. And in technologies like Java, garbage collection will come into picture, which will further halt and degrade the performance of the system. So this is how memory limits scalability. Now let us look at the how scalability is limited by the disk input output operations. How scalability is limited by the disk input output operations. So throughputs and input output operations. So storage devices, they have fixed the limits on how many input output operations per second they can handle. So see, storage devices, we make use of storage devices. They have fixed the limits on how many input output operations per second they can handle. Now heavy read write operations, because when the load will increase, heavy read write operations will take place and they will saturate these limits, and that is the bottleneck. And here latency will also come into picture. So mechanical drives, they have high seek times. Even with SSDs, if the application requires constant disk access, the CPU must wait for the data to return, stalling the entire process. So this is the disk IO bottleneck. So the idea is that when the load will increase, there will be more pressure on the disk, because of which the read write operations, it will further slow down and the performance of the system will degrade. So latency will come into the picture, and this is how the disk IO, it limits the scalability, because after a point of time the system will not be able to further scale, further handle load. The system will break down. Network bandwidth. So now let us see how scalability is limited by the network bandwidth. How scalability is limited by the network bandwidth. Let us see how scalability is limited by the network bandwidth. Transfer limits. So see, in network also there is a transfer limits are there. So network, it is the bandwidth of the network is limited by the capacity of the network interfaces to the transfer. Like it can be 1 Gbps or 10 Gbps. If the volume of the data being moved, such as video streams or large API payloads, exceeds this capacity, packets are delayed or packets are dropped. So that's the transfer limits. Latency and congestion. Beyond raw bandwidth, the time data takes to travel between nodes, that is called as the latency limits. Latency, it limits how quickly a distributed system can sync. High traffic can lead to congestion, where network devices become the bottleneck. So now it's very clear that when the load will keep on increasing, so when we talk about the network, transfer limit is there. The transfer limit can be either 1 Gbps or 10 Gbps. It cannot be more than that. So when the load is increasing, it has to wait because the bandwidth, it cannot support more than 10 Gbps of data transfer. So that's the bottleneck. And also latency and congestion will come into the picture. So latency is basically the time taken to travel, and high traffic will lead to high congestion. So when the load will increase, latency will increase, congestion will increase, and after a point of time, the system breaks. So network bandwidth, it limits the scalability. Now let us see how scalability is limited by the database contention. How scalability is limited by the database contention. So locking. So the idea is that to maintain data integrity, databases uses locks during write operation. So that if many processes they try to update the same record simultaneously, they must wait for the lock to be released, creating a stop and go effect that limits the throughput. So this locking is very important because when multiple processes tries to update the same data, they cannot update it simultaneously. So there is a concept of lock. So if the data is locked, it means somebody is trying to update it. And once the lock is released, then we can also update it. So this locking, it introduces the stop and go effect and it affects the throughput. And when the load will increase, when the load will increase, this throughput, it will further degrade because many more processors, they will try to access the record, update the same record. Connection pools. So databases have a maximum number of concurrent connections which it can support. Once all slots are taken, new requests from the application layer are rejected or queued. Centralization. A single non-sharded database often becomes the ultimate single point of failure for scalability as it cannot be easily split across multiple servers without significant architectural changes like sharding or replication. So now this is very important. Single non-sharded database, it becomes the single point of failure. Because of centralization, if you just use one database, if that fails, the entire system will collapse. And it's difficult also to distribute the databases because then we have to do that sharding, replication. So centralization is also a bottleneck because when the load will keep on increasing, we have to distribute the database. We have to balance the load because the single central database will not be able to handle the load. So now it's very clear that when the load will increase on the system, database contention will be a bottleneck. More locking will be there. Uh, Database, it has a maximum concurrent connections it can support. So after a point of time, it may not handle more connections, and centralization in itself is a bottleneck. So this is how database contention, it limits the scalability. So every system has a weakest link, and this weakest link is the one which gets breakdown on increasing the load. So every system has a weakest link And scaling means identifying bottlenecks and removing them iteratively. So scalability is all about identifying the bottlenecks and removing them iteratively. Like if CPU is the bottleneck, we can either go for vertical scaling or horizontal scaling, wherein we can either increase the CPU power or we can introduce more CPUs. So this is how we are. So the idea is that you are designing a system. You have to identify the bottleneck, whether the bottleneck is the CPU, the memory, the disk IO, the network, or the database. So identify the bottleneck and remove them iteratively. And in this way, you evolve the system. And as the system is becoming more and more scalable, it is handling more and more load, a new kind of a bottleneck you might identify. So the goal is we have to keep on watching the system, identifying the bottlenecks and removing them iteratively. And in this way, we can achieve scalability. Now let us look at horizontal versus vertical scaling. So if we look at the difference between horizontal scaling and vertical scaling, so in vertical scaling, we consider bigger machine. In vertical scaling, we consider bigger machine. So vertical scaling, the idea is that whatever machine we have, we add more compute power to it, more memory to it, add more resources to it. So that is vertical scaling. So vertical scaling is simple, but it is limited. And main limitation is the hardware limitation. Because if we talk about RAM, from 8 GB we can go to 16 GB RAM. But from 16 GB to 32 GB RAM, if I go, then maybe the motherboard I have to change, or some architecture I have to change. So that's a hardware limitation. So vertical scaling, it is simple, but it is limited. And the main limitation is the hardware limitation. So that is the vertical scaling wherein we add more power, more resources to the existing hardware. So if we look at horizontal scaling, horizontal scaling means replicating the machines, adding more machines. So horizontal scaling means adding more machines, replicating the machines. So horizontal scaling, it is complex because see the idea is that in horizontal scaling we are achieving a distributed architecture wherein we are having the replicas of same machine and we have to do the load balancing and some kind of a synchronization. So distributed architecture concepts will be involved and hence it is complex. But it is not limited. It is potentially unlimited. This is something very interesting about horizontal scaling, wherein with load, we can just keep on adding the replicas of the same machine and we can very easily scale. So potentially it is unlimited. So horizontal scaling means adding more machines, creating the replicas of the machine. It is complex because it involves distributed architecture, data consistency, load balancing will come into the picture, but it is potentially unlimited, wherein we can keep on adding more and more resources to achieve horizontal scaling. Now let us look at the key trade-offs. So in vertical scaling, we achieve simplicity, but in horizontal scaling, we achieve scalability. So in order to truly achieve scalability, we should consider the horizontal scaling and not vertical scaling. So finally, we completed this lecture. So in this lecture, we saw that scalability is not equal to performance. There is a difference between scalability and performance. We saw that scalability is not equal to efficiency. There is a difference between scalability and efficiency. We also saw that statements like system supports millions of users is meaningless without context. Scalability is all about handling growth. Systems evolve through stages. We don't design systems to handle millions of users from day one. Rather, systems they evolve with time. They evolve through stages, growth stages, and bottlenecks define scaling limits. So scalability is not a property you install, it is a property you continuously engineer. So I hope you got a very good understanding of the concepts which we covered in this lecture. So do subscribe to this YouTube channel, Scale Up University, for more such interesting lectures and courses. Thanks for watching. Thanks for your time.